Okay, welcome back. So we're continuing with op-amps. We'll see a few more op-amp circuits. I'll solve a couple of problems for you. And I did want to note again, kind of reiterate about those power rails. We have to make sure that our inputs and expected outputs remain within those power rails. In this first example, we have 0 volts on the negative rail and plus 5 volts on the positive rail, and 2 volts on the input is well within this range. And this circuit is just simply a voltage follower or analog buffer or unity gain non-inverting amplifier, like I mentioned last time. So we're getting 2 volts out and 2 volts as well within our range as well. So this case, it's good. However, on this bottom one, we have negative 21 volts feeding in, and note that the op-amp is powered from 10 volts to minus 10 volts. Generally speaking, this is bad. Is this op-amp going to break down? Probably. However, it does depend on the specific op-amp you're using. Now, for the sake of this class, I'm not going to go into specific op-amps. However, if you're looking for some op-amps to play around with or to use in future projects, let me go ahead and list a couple of the specifics. We have the 741, which is kind of that old classic. We also have the LM358, seems to be super popular. There's also the 324, which is actually one chip with 4 op-amps in it. And my personal favorite is the TLV 2372. This one down here is kind of a newer offering. These other 3 are sort of classics that have been around for quite a while. But the TLV 2732 is a pretty good op-amp. If you can get your hands on a few of them, you could definitely use them in future projects, especially your embedded systems classes. This is my personal favorite as far as a go-to jelly bean component that I just keep them lying around, and I tend to use them again and again. Okay, but yeah, going back to this, this is generally not a good thing. What is Vout going to be? Well, let's just say in an ideal sense where this op-amp doesn't break down, given an input of minus 21 volts, as I said, the breakdown could occur, but it depends on your specific op-amp that you're using. But Vout would go as low as it possibly could, right? The expected output from this voltage follower would be negative 21 volts. But as you can see, the lowest voltage that we can achieve on that output is minus 10. So Vout in this case would be minus 10 volts. Okay, now last time, I don't think I showed this image. When we're working with op-amps, we're always drawing this triangle over here. But one thing that I did want to emphasize is these are not simple components. These aren't like, it's not like a resistor, and it's not even like a transistor. It's actually a lot of transistors. Anywhere from, let's say, 10, 11 to 22 transistors it takes to actually make one of these op-amps. So I do have a schematic here for what's going on the inside. I'm not even going to bother trying to explain this. When I was taught op-amps, we were actually shown an image similar to this, and we went through the whole thing, and afterwards I still didn't know how an op-amp operated. So I teach op-amps from the overview perspective, those fundamental rules that allow us to analyze all the op-amp circuits. As I said, it is applicable 99.9% of the time. It will get you the right answer. There are some really creative, interesting uses of op-amps that do not fall into that category. They're extremely rare. You'll probably never come across them. But just to give an overview, this is what's going on inside. As you can see, it is a lot of transistors, and we have kind of like this differential input side, and op-amps come in thousands of different varieties specialized for different purposes. I listed just sort of the jelly bean parts that are pretty common and great go-tos when you need to use an op-amp for the functionality of your circuit. But let's go ahead and let's get into a couple of the other really common examples of op-amp circuits. All right, last time we went over the non-inverting amplifier. I like to cover that one earlier because it's a little simpler in some ways. But let's go ahead, let's look at the inverting amplifier. Now, if you notice, the positive input, or the non-inverting input, is tied to ground. Our signal comes in on Vin over here attached to an R1. That feeds in directly to the inverting input, and then we have this feedback resistor connecting the output back to the input. So we have a loop, we do have a closed loop circuit here. We have some pathway for the input to be affected by the output. Therefore, rule number 2 applies here. Now, let's go ahead and let's just look at the equation for a second. I'll also note over here, I do have this drawn where I have it kind of with this second ground connection over here. Don't read too much into that. This is, I'm just saying that Vin as a voltage is referenced from ground. So all of these have the same ground attached to them. That's true for all of the circuits we've encountered. The equation that we use for this, I have it written over here as the gain, the voltage gain. And the voltage gain, you could have written this out for the previous non-inverting one as well. However, I'm highlighting it here for the inverting amplifier, that the voltage gain is determined by the feedback resistor divided by R1. And then that whole thing is negated. This negation is the inverting aspect of this amplifier. Now, one of the things you'll notice on all of your op-amp circuits, generally, when the input is tied somehow to the negative rail, you get an inversion. Meaning, if I give a positive voltage here, I get a negative voltage over here. Similarly, I put a negative voltage on Vin, I get a positive voltage on the output. Okay, and in the previous non-inverting, you'll see that that signal was tied to the non-inverting side. Okay, so looking at where your signal connects to actually gives you an indication whether you're going to get an inverting type of amplifier or a non-inverting type of amplifier. So that's why we end up getting this minus over here. But if you use those two rules, you're going to get the right answer anyways. So I don't get too hung up over the signal being tied to the non-inverting or inverting. Those rules will work no matter what. Okay, so as it looks like, our Vout is Vin times our gain, right? And that's what you would expect from an amplifier. Gain times your voltage input. And the gain here is determined by the ratio of the feedback resistor to R1 over here. So let's go ahead and let's go ahead and draw our inverting amplifier over here. Vin, I'm going to make it equal to 2 volts. I'll make R1 equal to 1K. And I'll make our feedback resistor equal to 2K over here. Okay, and we can solve this using our basic rules, or we can go ahead and memorize the equation, which I promise you'll forget that. But let's go ahead and let's solve out the equation for this circuit first, and then we'll check it using our rules. Okay, I'm going to go ahead and write out the equation for this circuit in general. Vin times a minus Rf divided by R1. Okay, what are we going to get? Well, we should get 2 volts times minus 2K for our feedback resistor divided by 1K. Okay, so what's our gain going to be equal to? Well, our gain is going to be minus 2K divided by 1K. That should be minus 2. Okay, so this whole term goes to minus 2. So we should be getting 2 volts times a gain of minus 2 equals minus 4 volts. Okay, that's our expected output. Can we get that just using our fundamental rules for op-amps? Of course. Okay, and hopefully it should turn out to be minus 4, but let's see what happens. Okay, rule number 1, of course, no current in or out of the inputs. Zero amps there, and 0 amps there. All right. Now, rule 2. Is rule 2 even applicable? Remember, rule 2 only applies when you have a closed loop of some kind. So if we have some way for the output to influence one of the inputs, then rule 2 is applicable. Well, what do we have here? We have a connection with just one resistor from the output to the inputs. Absolutely, rule 2 is applicable. That means rule 2 is going to, the op-amp will do whatever it has to make these two inputs be the same voltage. Do we know what one of the voltages on one of these inputs is? Yeah. Look at this. The non-inverting input side is tied to 0 volts. We have 0 volts there. So what does that mean that the voltage at this point should be? Well, it should be 0 volts as well. That's what the op-amp's going to do. Now, can we trace it back to Vout and find out what Vout is? Yeah. Well, what's the first thing we can solve for here? Notice we know what Vin is. We have 2 volts on this side, and we have 0 volts over there. Current always flows from higher voltage to lower voltage. So we have current going in that direction. How much current? We'll just use Ohm's law. We have 2 volts across this 1K, and we have a resistance of 1K. So just use Ohm's law. 2 volts divided by 1K equals what? It should be 2 milliamps, right? Now, notice we have 0 amps entering or leaving this input of the op-amp. And I should have drawn this arrow a little closer to here, because remember we have a node right here. So we do have current flowing through that little section of wire, and it's going up. Now, KCL says we have 0 amps going this way, and we have 2 milliamps entering. So what should we get? Well, we should get 2 milliamps going through that 2K. So let's draw that in. Now we know we got 2 milliamps flowing through the 2K, so we can solve for the voltage drop. We know the resistance, we know the current. V equals IR. I is 2 milliamps, R is 2K. So 2 milliamps times 2K should be what? Well, 4 volts, right? Okay. So we have 2 milliamps times 2,000. We have 4 volts. But notice the direction of the current. Current always flows from a higher voltage to a lower voltage. Therefore, we drop 4 volts across this 2K, but on this side we're 4 volts lower than 0 volts. Okay, so I use the direction of the current to tell me the polarity so I can figure out which side is the higher voltage potential. So 0 volts must be higher than this. By how much? By 4 volts. So this should be minus 4 volts over here. V out, therefore, is equal to minus 4 volts. And that's exactly what our equation gave us. Okay, so no need to memorize all of these equations. You can always just use those basic rules and arrive at your answer that way. Okay, so that's our inverting amplifier. We gave it a positive 2 volts, we get out a negative voltage. So it got inverted. And it's an amplifier. We gave it a gain of 2 in this case, because the gain was determined by the ratio of our feedback resistor to our R1. Okay? So that's our inverting amplifier. Okay, so just to recap, what circuits have we gone over with op-amps? We saw a comparator. We saw a voltage follower. We saw a non-inverting amplifier. And we saw an inverting amplifier. Okay. In my opinion, using op-amps tends to be a lot simpler and ultimately a better solution than trying to create your own transistor amplifier, like the common emitter amplifier. And it's actually better in many other ways, because we are guaranteed to have a high impedance input and a low impedance output, guaranteeing that we don't squash our signal without even having to worry about it. We don't have to calculate the impedances for it. So, I mean, from a utilitarian point of view, op-amp is a great fundamental block for many of your circuits for any time you're interfacing to an embedded system. Anytime you're interfacing to an FPGA or a microcontroller. So you'll find in properly designed schematics and proper designs in general that almost every single analog input that ever gets used on a microcontroller or FPGA or your analog digital converter, if you have an external one, is going to have some signal conditioning that gets performed before you actually reach that analog digital converter. And I've never created one that didn't use an op-amp, because as I said, even a voltage follower is very useful for fixing that problem of impedances. Okay, so this is what we've covered. We do have a couple of others. Now, this next one I think is going to be neat, because we're going to be able to perform mathematical operations at this point. We're going to be able to add voltages. which we've never done before. Now, one thing that we need to look at before we look at how the summer works. A voltage divider again? Really? Can I actually do a circuit without involving a voltage divider? I don't think so. This circuit is everywhere. Okay, what's going on here? Well, a voltage divider. We divide our input voltage down to something else. In this case, if I pick both of my values to be the same, so 1K and 1K, or 100 ohms and 100 ohms, or 100K and 100K, I will always get half of my input voltage, right? Okay. So if I put 5 volts in, I get 2.5 volts out. Now what happens if I change this ground over here to another voltage? Well, I get what's referred to as a passive averager. In other words, it takes the average between the two voltages. And that makes perfect sense. I've redrawn this to treat it more like I have two input voltages and one output voltage. But it is the same circuit. I'm just changing what this point is. Instead of tying it to ground, I'm tying it to another voltage. And when I do that, and I keep both of these values the same, I'm always going to get halfway between my two input voltages, right? Over here, the same thing is true. 5 volts over here, 0 volts over here. Halfway between those is 2.5 volts. Well, if I change the ground, the same is true. If I put 3 volts here and 2 volts here, I'm going to get 2.5 volts on the output. And you can solve this just using your basic rules as well. I have 3 volts over here, 2 volts over here. The difference between them is 1 volt. I have two of the same valued resistors, and I have 1 volt across both of them. I should get a 0.5 volt drop across this 1K and a 0.5 volt drop across this one. So at this point, I should be 0.5 volts less than the 3 volts and 0.5 volts above the 2 volts. So the passive averager just leverages a voltage divider to do what it does when we give it two of the same valued resistances. Now, if I can find the average between my two input voltages, and I know that I have two inputs, can't I just multiply this by 2 in order to get an output of 5? And wouldn't that be the addition of 3 volts to 2 volts? That's how I'm going to go ahead and make this summing circuit. So what I've done over here is I'm combining my voltage divider, or in this case, a voltage divider used as a passive averager, and I'm using a non-inverting amplifier with a gain of 2. Remember that your non-inverting amplifier has a gain of your resistances divided plus 1. So in this case, 1K divided by 1K is 1, plus 1 gives us 2. So I'm amplifying whatever I put on this non-inverting input, I'm amplifying it by 2, which would be 5 volts. So this is a really cool circuit when I want to add up two voltages. In fact, I can't think of any other way to do that. This is the only, I'm sure there's other ways, but this is the one that I would go to when I want to add up two voltages. I can't say that that comes up really frequently. I've actually used it in a couple of designs when I was adding up outputs from sensors. So you can think that I have one sensor here and another sensor there, and I wanted to add those up before they go into the microcontroller. So it does get used. I just wanted to show one example of an op-amp circuit that performs a mathematical operation. And I think this is a great, simple example that shows combining these basic circuit elements to get something pretty cool, in my opinion. So over here are passive averagers, taking the average between both of these, and the average times 2 gives us the addition of both of these. Okay, so there's another circuit. And if you go back to the previous video, you can see the analysis for the non-inverting amplifier. And really, this is just an extension using that passive averager on the front. Now, I'm going to show this one, but I won't be testing on it. You can add up as many voltages as you want. And in fact, this was the version that I've used in previous circuits. I haven't come across the case where I needed to add 2 voltages. I have come across the case where I needed to add 3 voltages before. Now, again, we can create a passive averager that averages 3 voltages. And if you wanted to solve for V out, look up Millman's theorem, and you can see how you can figure out what V out is for 3 voltages. This is the equation that Millman's theorem pops up with. And if we set R1 equal to R2 and R3, we then get an averager that gives us the average between whatever 3 voltages we put in. So it's the same concept as the passive averager on the previous page. This is just a passive averager with 3 inputs. Again, we would do the same thing, except now we need to multiply this by 3 in order to get our summed output. So again, the same exact circuit. It's just the passive averager has changed, and we've adjusted the gain of the amplifier in order to give us an amplification with a gain of 3. Okay. Like I said, I won't be testing on this, but I wanted to show it anyways. Okay, so now we've gone over the comparator, the voltage follower, the non-inverting amplifier, the inverting amplifier, the summer, and there is one last one, which I personally think is the best, most useful circuit with op-amps for us. Now, we haven't even really scratched the surface of op-amp circuits. There's quite literally volumes of texts on all of the different things you can do with an op-amp. They quite literally are one of those fundamental building blocks of analog circuits. But the more specificity, the more esoteric designs, we just don't have the time or the scope in this class to cover all of them. But anytime you need to change a voltage before you put it into a digital system, look at an op-amp to be able to solve it. Now, the last one that we're going to look at is going to be the differential amplifier. I think between all of these, we've covered all of our bases for making useful op-amp circuits to get the job done when we need to later on in our classes or in the workplace. if we know these, we're going to be quite comfortable working with electrical engineers in the workplace. But this last one, I really think is one of the more useful, really extremely useful ones. And definitely there will be a question regarding the differential amplifier. There will be a circuit to solve. So let's get on with it. So this one will 100% be on the exam. Okay, this is our differential amplifier. Now we have an R1 and we have another R1. Now when we write two R1s in the same circuit, it means they have the same value. So if R1 is 1K, R1 over here is also 1K. Similarly with R2 and R2, if this was 4K, this would also be 4K. Now, the equation that tells us the output is the difference between our two inputs. We have a V1 here and a V2 here. So we're taking the difference between both of them, and then we're multiplying it by our gain. Our gain is just dictated by the ratio between R2 and R1. So let's go ahead and let me draw this one out. And we'll do an example. We're actually going to do two examples with the differential amplifier. It's worth it. Okay, we're going to have a V1 equal to 1 volt. We're going to have a V2 equal to 3 volts. R1, R1, and R1. Make sure that's a 1. R2 and R2. And the out should be V2 minus V1 multiplied by R2 over R1. Now, let's go ahead and let's give ourselves a desired gain that we want. We're going to want to gain a 2. So what we're going to be doing is taking the difference between 1 volt and 3 volts, the difference being 2 volts, and 2 volts times a gain of 2. So we just need to pick R2 to be equal to twice that of R1. So I'm going to go ahead and make R2 equal to 2K, and I'm going to make R1 equal to 1K. Should give us a gain of 2. 2K divided by 1K is 2. 2 times the difference between that. So our expected output, if the difference of our two inputs is 2 volts, and we multiply it by a gain of 2, we should get 4 volts on the output. At least that's what our equation tells us. Let me write in the values over here. 1K, 1K, 2K, and 2K. All right. Can we solve this? Where do we even start if we're going to solve this using our fundamental rules of Opamps? Well, I know this voltage, I know this voltage, I know the values. Do I know this voltage? Well, yeah, using my equation, but I'd like to solve this without using an equation. So where can I start? Let's just start asking ourselves some questions. Okay, rule number 1. No current in or out of the op-amp. All right. 0 there. 0 there. Does that help? Actually, it does kind of help us. What do I have over here? I got 0 volts here. This means the current never goes over here, right? Look at KCL. Look at this node. I have some current. Well, which way is it going? I got 3 volts here, 0 volts there. Current goes from a high voltage to a low voltage. And these two are the same. They have to be. No current's leaving. This is just a series circuit. Wait a second. I know this circuit. What? Again. A voltage divider. Okay. 3 volts here, 0 volts here, 1K, 2K. Can I figure out what the voltage is over here? I can use my basic rules, figure out what V out is. Take 3 volts divided by 3K. That gives us 10 milliamps. Oh, let's just do that. 10 milliamps. And I got 10 milliamps going. So I drop 1 volt here. And I drop 2 volts there. So what's V out equal to? Well, if I'm at 3 volts, Kirchhoff's voltage law, I'm at 3 volts, I drop 1 volt, I must be at 2 volts. Or you could have just gone ahead and done V out is equal to V in times R2 divided by R1 plus R2. You'll get the same value. Okay, voltage divider. Really should have this equation memorized by this point. Okay, so we know now that this is 2 volts. Well, what's the second rule about op-amps? Op-amps going to be, in the presence of having a feedback, which we do, we have a pathway from our output back to one of our inputs. It will do whatever it has to make both inputs of the op-amp equal the same voltage. So I have 2 volts over here. I must have 2 volts on this wire. Now I can figure out my current for R1. Current always goes from a higher voltage to a lower voltage. Okay, what's my voltage drop across R1? In other words, what's VR1? Well, I have 2 volts on one side, I have 1 volt on the other side. I have 1 volt across R1. So now to figure out my current, I can just say 1 volt divided by 1K equals what? 1 milliamp. Okay, I know where my current is going now, and I know that this is 0 amps in or out of the op-amp input. So this 1 milliamp must be coming from here. KCL, by the way. And I have 1 milliamp flowing through a 2K resistor. Can I figure out my voltage drop? Absolutely. It is 2 volts. Do I know my voltage at this point? Yeah, it's 2 volts. Right? Because the op-amp's keeping these both inputs at the same voltage. So, look at my current direction. This side must be higher than this side. Current always flows from a higher voltage to a lower voltage. And it's dropping 2 volts. So this side must be 2 volts higher than our 2 volts over here. Means I must be at 4 volts. And that is what we solved for. Okay? So, absolutely, our basic rules for op-amps work in this situation. And the equation. Now, I will say, this is one equation I keep memorized because of how valuable this differential amplifier is. And you don't have to take my word on it. We're going to see why it's so important after, well, right now. Okay, so let's define some problems, something we want to design. Let's say we want to design an embedded system that measures current 0 to 10 amps. Now, why would we ever want to do this? Well, let me go ahead and give you some reason why we might want to measure current. Let's say we're making an escalator. Okay, you know escalators, those things that go in a mall and they lift you up. Not an elevator, escalator. And in that escalator, obviously you have some motor making the escalator turn. And let's say the escalator motor, I'll make it as simple as possible. We just have some VCC attached to some motor. Obviously there's some other stuff to turn the motor on and off. But that would be our simplest circuit driving a motor. Now, let's say someone were to get their foot stuck in an elevator, or a hand, or some object. The motor is going to stall. Now, do I want to keep this motor on? Probably not. I'd like to detect when some foreign object has made its way into the escalator. Now, one of the neat things about motors they have to do some work. And as that work goes up, the amount of current goes up. So if I want to detect if an object has lodged itself in here, as the motor works harder to try and chew up that object, the current that this motor is using will go up. And this is true of all motors. As the load increases, the current consumption of this motor increases. So we need to measure the current going through this motor. Now, to draw that in a schematic form, typically we'll just do something like that. We'll put a loop around this wire to indicate that we're measuring the current flowing through this wire, which is the current flowing through this motor. And if you're using LT Spice, you'll see that the current measurement tool also looks like a little ring around the wire. So what we need is a current sensor. I'm going to sound smart and call it a transducer. We need a current transducer. And that current transducer is going to give us a voltage proportional to the amount of current that's flowing through this. And if that voltage reaches some threshold, we can indicate from the microcontroller, hey, turn off the motor, something got stuck in there. We can have some sort of fail-safe to prevent injury on this escalator. So we're going to make a safe escalator. So we're going to need a current sensor. So we go out to purchase a current sensor. And as it turns out, we can't find a current sensor that measures from 0 to 10 amps. Let's just say 10 amps is quite small for the motor of an escalator, but just bear with my analogy. We want to measure, and let's just say normal operation is 0 to 5 amps. So we get a current measurement that does 0 to 10 amps. That way, when it goes above 5 amps, we can trip a fail-safe and turn the motor off. But when I go to DigiKey and try to purchase a current sensor, I can't find one that does 0 to 10 amps. Instead, what I find is one that does minus 10 to plus 10 amps. And I'll give a couple of different points in this range. I'll do minus 10 amps, I'll do 0 amps, and I'll do plus 10 amps. Now you might ask, well, why does the current sensor do minus 10 amps? Well, in case the current starts going in the other direction. Okay? Current sensors, it's useful to know the direction of the current as well. So I buy a current sensor, but it only goes minus 10 to positive 10. And the sensor gives me a voltage output proportional to the amount of current. And at minus 10 amps, it gives me 0 volts. At 0 amps, it gives me 0.5 volts. And at 10 amps, it gives me 1 volt. Now, in our design, we're going to take this current sensor and we're going to feed it into the analog digital converter of some microcontroller unit. Very common. This is something we do all day long. And so the ADC going into the microcontroller measures some range of voltages. So I'm going to list the ADC over here. And the ADC has a VIN, and it also gives me a converted value, a converted digital value. And let's say 0 volts gives me an 8-bit value. So let's just say this is an 8-bit ADC. And it does 0 to 5 volts. So 0 volts should get converted into 0 decimal. 0.5 volts will get converted into 26 decimal. 1 volt gets converted into 102 decimal. 2 volts gets converted into, this is 51. 2 volts gets converted into 102 decimal. 2.5 volts, 128, and 5 volts, 255. Okay, so I've established the output from my sensor, and I've established the range of inputs for my analog digital converter. How I got these values just comes from calculating the step size for an 8-bit ADC, given the range of 0 to 5 volts. Go back to that video. Now, here's my dilemma. My system only does 0 to 10 amps. That means within the entire operating range of my system, 0 to 10 amps, that's what I defined. I want my embedded system to measure 0 to 10 amps. So I only care about the sensor's output from 0 to 10 amps. And similarly, if I feed this directly in to my ADC, I will get an expected value of 26 decimal to 51 decimal. That's if I put a straight line, a straight wire connecting the sensor directly to the ADC. However, notice all of the values that I don't get to use. I'm going to lose everything below 26, and I'm going to lose everything above 51. So on top of my analog digital converter only being 8 bits, I'm losing all of this range. This is all useful input to my analog digital converter. So what if I want to make an amplifier? If I make an amplifier, I can go ahead and change this range so that 0.5 volts gets converted into 0 decimal and 1 volt gets converted into 255. So what I want to do is some type of amplifier buffering the sensor output and the analog digital converter input. That way I'm not wasting all of this range. Okay? So that's our goal here for this amplifier. I want to change the voltage output so that 0.5 volts gives us 0 volts, which would give us 0 base 10. And I want 1 volt. 1 volt's the upper range of my expected sensor output. And I want to turn that into 5 volts. So that my converted value is the full range of my analog digital converter. That way I don't have to sacrifice and lose all of this precious resolution, right? Instead of my digital value now being 26 to 51, now I get 0 all the way to 255. That's like a 5 times improvement on my resolution. Now, here's the thing. I can't just use a non-inverting amplifier because 0.5 multiplied by anything greater than 1 is not going to be 0. So I need amplification and offset. The amplification I get from a non-inverting amplifier all day long, but I can't change what my 0 point is. But with a differential amplifier, I can. So let me show you what this circuit is going to look like. I would like an offset equal to 0.5 volts. In other words, I want to subtract 0.5 volts from the sensor before I do any amplification. And then I want to amplify it so that the difference between 0.5 volts and 1 volt gives me 5 volts. Now the difference between 0.5 volts and 1 volt is 0.5 volts. So 0.5 volts times something is going to give me 5 volts. That something's going to be 10. So this is what we need to do. Offset by 0.5 volts and amplify by 10. Well, the differential amplifier is going to be the only circuit element that allows me to do this. So let's go ahead and draw our differential amplifier. I already wrote down one of my values. Now let's go back to the equation, and I'm going to use the equation for this one. V out equals, well, where's our equation? V out equals V2 minus V1. Which one's V2 and V1? Well, V1's over here, and V2's over here. V2 minus V1 times our gain. Well, we know that this is our gain. It's the ratio between R2 and R1. in other words 10. But if I want a sensor output from 0.5 volts to get turned into 0 volts, I need to subtract 0.5 volts from our sensor voltage. Therefore, V1 is going to be a fixed constant 0.5 volts. V2 is going to be our sensor voltage. I'll call that V sensor. Okay, so V2 is V sensor. V1 is going to be a constant (0.5 volts. And I need to set this up such that my gain, R2 over R1, is equal to 10. So I just need to make R1 1K and R2 10K. That'll give me that. R2 will be 10K, R2 will be 10K. R1 will be 1K, R1 will be 1K. And I think I got it. I think this will work. Let's double check this. We want 0.5 volts to get turned into 0 volts, and we want 1 volt to get turned into 5 volts. So I'm hoping that this ends up being true. So let's go ahead and let's solve it for 0.5 volts. V out equals V sensor, which is 0.5 volts, minus V1. V1 is our constant 0.5 volts. And our gain, the ratio between R2 and R1, is 10. What does that give us? Well, 0.5 minus 0.5 is 0. 0 times anything is 0. All right, so this first line seems to be true. What about 1 volt? Will 1 volt get converted into 5 volts? Well, let's check. V out equals 1 volt minus a fixed constant 0.5 volts times 10. Well, this equals 0.5 volts, and 0.5 volts times 10 is 5 volts. Very cool. Okay, so now I have a differential amplifier that I can put right here. And when I do put the differential amplifier over here, I now get to scale my expected values of 0.5 volts or 0 amps to 1 volt or 10 amps, and I get to scale that so that I use my intended full range of my ADC. And this is how you properly design the analog stage for an analog digital converter. You want to maximize this range so that you're using all of the resolution of your ADC. I don't want to waste everything below 26, and I don't want to waste everything above 51. If I didn't use some differential amplifier in here, I would have to do my computations for detecting when the motor stalls or when something gets stuck in the escalator. I would have to detect that between 26 and 51. That's a very small range. I'm going to get much better results if I can use the entire range of my ADC. So, not only did I get to use my entire resolution of my ADC, but I also fixed the problem of impedance issues going into my microcontroller. So this really is the proper way to go ahead and solve this type of a problem, and in fact it might be the only way. Well, no, I won't make a blanket statement like that. It's going to be the only logical, practical way that you would do it at the workplace. Depends on everything else in the circuitry. But this would definitely be the most practical first approach for solving this type of a problem. Okay? So I know that that's quite a bit in that problem, and there is a little bit of philosophy when we get into looking at that resolution and losing out that all of those values above 51 and all of those values below 26. But I wanted to show how powerful and why this differential amplifier circuit, why I say it's one of the top ones that you should have in your arsenal, right? We're all building up a kit of tools to solve problems, and for getting signals into digital circuits, this is one of the more powerful and more popular ones. And it only costs one op amp and a couple of parts to throw in there, and you get a lot of bang for your dollar this way. Okay? So please, practice this problem. Okay, so I'm going to go ahead and solve an amplifier circuit, and this amplifier circuit looks quite intimidating. Oh wait, there's our amplifier circuit, op-amp circuit. Okay, so at first this looks intimidating, but I promise you with just our basic rules and knowing what we're doing, we're going to be able to step through this and find out what Vout is, no problem. So let's go ahead and start filling this out, and let's just step through it. Okay, V1 is going to be 3 volts. R1, what's R1? Looks like all other resistors are 1K. Okay, so if it's not specified up here, it's 1K. R9 is 2K. R3, that's the only one that's specified. Okay, so all of these are going to be 1K. 1K, 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 and 1K. V2 is going to be 12 volts. And V3 is going to be 0 volts. Okay. Now, how do we go ahead and solve this? Well, what are we solving for? I'm going to do it when switch 1 is placed on B. So I'm going to cross that out. The selector switch is on B. And we're going to go ahead and solve this. Okay, what do I have? Well, in order to solve any of these op-amp circuits that have a closed loop of some kind, you can see that we have our feedback over here, but it goes through all of this nonsense down here. And it looks like it'd be incredibly difficult to solve. In order to get that, we're going to have to use the rule 2. And that means we're going to have to find out one of the voltages on one of these pins. Now, over here, I'm not going to be able to figure any of this out, because in order to figure this out, I need to know the voltage over here, but the voltage over here is a function of over here. So I'm going to need to work this way. Okay, seems like it's not a problem. Rule 1 of our op amps is no current in or out. Zero amps there and 0 amps here. Okay, well that kind of gets us started. If we have no current flowing through this 1K, can we figure out what the voltage at B is? Yeah, absolutely. We just have a voltage divider with 3 volts and 0 volts over here. Okay, so let's figure out the voltage at this point first. So we'll use our voltage divider equation, make quick work of that one. So we have 3 volts times R2, which is 2K, divided by R1 plus R2, so 1K plus 2K, which is 3K, equals what? Okay, well, let's do that. 3 times 2,000 divided by 3,000 gives us 2. Okay, so I have 2 volts here on this wire. I have no current going through this resistor, so I get no voltage drop across R3. So if I have 2 volts here, I should get 2 volts over here. If I have 2 volts over here, then by rule number 2 of our op-amp analysis rules, I should have 2 volts over here. If I have 2 volts over here, and ground over here, well, what do I do at this point? How much current do I have going through R4? Well, remember, I have 0 current going in or out of this op amp over here. So I have 0 amps going through R4, which means VR4 is equal to 0 volts. I have 2 volts on this side. I drop 0 volts. I have 2 volts over here. Now I can go ahead and solve for the current going through R5. I have 2 volts here, I have 0 volts over here. Current always goes from a high voltage to a low voltage. And I have a 2 volt drop across the 1K. So the current magnitude is just equal to 2 volts, the difference between these two, divided by 1K. 2 volts divided by 1K should be equal to 2 milliamps. Now look at this node over here and look at KCL. I have 0 amps leaving or entering this node, and I have 2 milliamps going down through this 1K. Where did that 2 milliamps come from? It had to come from over here. Can I figure out the voltage drop across R6? Absolutely. VR6, just use Ohm's law. V equals IR, and I is 2 milliamps, and R is 1K. So 2 milliamps times 1K is just 2 volts, right? Now I drop 2 volts across this resistor, and current always goes from a higher voltage to a lower voltage, so this must be 2 volts higher than 2 volts over here. So I must be at 4 volts right here. Now I don't know what's happening in this area yet, but I have 4 volts on this side, I have 0 volts on this side. So I just have 4 volts dropped across this 1K, so I can figure out the current. Current I know is going down because 4 volts is higher than 0 volts. Current always goes from a higher voltage to a lower voltage. 4 volts divided by 1K, Ohm's law should give me this value. Should be 4 milliamps. Now let's look at KCL. I have 2 milliamps going this way, 4 milliamps going that way. I must have 6 milliamps going through this 1K, which means the voltage drop across R7 should be 6 volts. I should be at 10 volts over here because I know that this side is higher than this side by 6 volts, so I should be at 10 volts here. V out is directly connected to this 10 volts, so V out is 10 volts. Okay, so it's not a bad problem, and it's definitely something that I would look out for on a future exam. Something similar to this. Now, I asked the question, what's V out when B is selected? But just as easily for when A is selected, I could have done the same thing. Only difference is it's now connected to 3 volts directly. So I go through the entire problem again with 3 volts over here. So I get 3 volts here, I must have 3 volts, and trace that all the way back. Okay, so it's an intimidating problem at first if you've never seen it. But once you're comfortable with those basic rules, solving this is a piece of cake. Now, let's go ahead and talk about things that you will probably see on the final. Okay, so this is going to be my final review. These are problems you're guaranteed to encounter. You're going to have a BJT amplifier problem, the common emitter type. Okay, I have a video solving one of those, and there's an example. If you look for the lab solution on the website, you're going to see that BJT problem solved. Look at that problem, compare it to the one from the video lecture. Compare those two. There's a subtle difference in those two problems. The video has one version and the website has a slightly different version. But they are essentially the same problem, but there is a minor adjustment to the equation. So be comfortable with both of those variants. There's an there's an ADC, an analog digital converter successive approximation problem. I may have put that into a video. In fact, it's probably this video. Differential amplifier problem. I also showed that problem. There's probably going to be a power supply problem. We did one of the quizzes on it, and we covered that a lot during the earlier portion in the in class. So besides these, what other things would you see? Now these all are have pretty good tips on where to look for these problems, so none of these should be a surprise. But there are a lot of other things that we covered. We covered BJT, base bias, and voltage divider bias. We learned two techniques to solve this, Thevenin and an approximation technique. Know those two. What else did we do with BJTs? Oh, definitely the mode of operation, of course. That's kind of a given in these problems. Mode, cue point, load line. I did show some switching circuits using a BJT. I used an LED, for example. Be comfortable with those. For the power supply problem that I mentioned earlier, obviously that's a given. Transformers, rectifiers, those types of problems. Of course, there's always the diode circuits. Clipper circuits, double diode clipper. Those are all kind of a given. There were MOSFETs. We only learned the MOSFETs from the using it from a switcher perspective. H bridges. There's some more BJT amplifier impedances, cascaded amplifiers, right? When we have one amp feeding another one, we get another voltage divider created by the impedances. We have some general op-amp stuff. Problem like this that we just solved. We also covered comparators, using an op-amp as a comparator, voltage followers, non-inverting, amp, inverting amp. What else comes to mind? Zener diodes. In AC, like those clipper circuits, or regulator. You can construct a regulator out of a Zener diode. We also had regulators. We covered the 7800 series, LM317s, the adjustable ones. I'm looking back through all of my materials